Welcome to Module 1 on gravitation. In this module, we will explore the history of gravitation, centripetal and gravitational force, the characteristics of gravitational force, the universal law of gravitation, and its importance. The study of gravitation began with Indian astrologer and mathematician Aryabhatta. He studied the motions of planets and stated that the Earth revolves on its own axis and moves in a circular orbit around the Sun. Ptolemy, active between 100 and 170 BC, proposed the geocentric nature of the universe, believing the Earth was the center around which the Sun, planets, and celestial objects revolved. Centuries later, Copernicus, from 1473 to 1543, disproved the geocentric idea. He introduced the heliocentric nature of the universe, where the Sun is the center, and Earth and other planets revolve around it. Galileo, later on, verified the Copernican idea about the universe after his persecution, supporting the heliocentric model. Tycho Brahe, from 1546 to 1601, significantly contributed by providing accurate predictions of the locations of stars and planets. Building upon this work, Johannes Kepler introduced his 3 laws of planetary motion, which are known as Kepler's laws. Finally, Newton gave the law of gravitation, based on Kepler's 3rd law, which is famously known as the Universal Law of Gravitation. Newton also described centripetal force. He stated that a force causing acceleration and keeping a body in a circular path, acting towards the center, is called centripetal force. The motion of celestial bodies and their attractions are subjects of long-time study. The force of attraction existing between all bodies in the universe is called gravitational force. Let's explore the characteristics of gravitational force. Firstly, it is a central force, meaning it acts along the line joining the centers of 2 bodies. Secondly, the gravitational force is a long-range force. It remains effective even across vast distances, as seen with the Earth and Moon. Thirdly, it is a conservative force. This implies that the work done by gravitational force depends only on the initial and final positions of the body, irrespective of the path taken. Unlike electrostatic and magnetic forces, the gravitational force is always attractive, drawing objects towards each other. The universal law of gravitation states that every object in the universe attracts every other object with a force proportional to the product of their masses. This relationship is represented by the formula F is proportional to m1 multiplied by m2. The force of attraction is also inversely proportional to the square of the distance between them. This is represented by F is proportional to 1 divided by the square of the distance d. Combining these 2 proportionalities, we arrive at the universal law of gravitation formula, F equals g times m1 m2 divided by d squared. In this equation, g represents the universal gravitational constant. It was measured experimentally by Henry Cavendish to be 6.7 times 10 to the power of minus 11 Newton meters squared per kilogram squared. The universal law of gravitation is important for several reasons. One of its applications is calculating the mass of the Earth. It also helps in calculating the mass of celestial objects, such as other planets. The law is crucial for discovering binary star systems in space. Additionally, the law explains the revolution of planets around the Sun. It also describes how we are able to stand firmly on the surface of the Earth. Furthermore, the universal law of gravitation explains the formation of tides due to the Moon's gravitational pull. Let's apply the universal law of gravitation to a numerical problem. We want to determine the force of gravitational attraction between the Earth and a 70-kilogram student at sea level. Using the formula F equals gm1m2 divided by d squared and substituting the given values, we calculate the gravitational force to be 686 newtons.